Hey class, we are almost done with the semester. Good job, way to hang in there. So I'm going to lecture a little bit on Unit 9 and talk about your homework questions for that unit. And yeah, that's kind of it. Oh, my automatic lights. It keeps happening in my office. Okay, sorry about that. Let me share my screen to the lecture, and then we're going to use JASP too, so make sure you have that downloaded. All right. Didn't look right. All right. Well, you can see this. That's your knife. So we had been doing t-tests, right? And so you had learned how to compare sample means to hypothetical population means. And then we talked about paired samples t-test, where you're comparing one student or one participant's data to their own data, right? They served as their own marker, and as opposed to samples to population means. But what if there are more than two data points that we're working with? So we're going to talk about multiple t-tests and then ANOVAs in this unit. So let's say scenario one, you have two antidepressants, Prozac and Elavil. Can we measure the difference in the effectiveness? We could randomly select 12 patients and give them to one of the two categories, right? Half of you get Prozac, the other half get Elavil. And then we could conduct our independent samples t-test. Easy peasy, that's what we've been doing the whole semester, right? Working up to that. But in scenario two, we have four antidepressants. We have Prozac, Elafil, Zoloft, and Trophanil. Well, how do we tell the difference in the effectiveness for those four? Because now we have six possible comparisons between the two, right? We could compare Prozac to Elavil to Zoloft to Tofranil and across the board, right? We can compare them to each other. So we can't do that with the t-test because now look how many comparisons we have down there. So we can do something called an ANOVA, or it stands for analysis of variance. Because if we just keep doing t-tests over and over again on those, we could increase the risk that we'll conduct type 1 error. Type 1 error is when we say that we found an effect, we reject the null, and we say that we found this effect or this difference that isn't really there. Whereas type 2 error is when we don't find an effect that was there. So if we failed to reject the null, but we failed to reject the null, but there was actually an effect. So those are type 1 and type 2 errors, and we don't want to commit either of them. And so when we're conducting multiple t-tests, doing an ANOVA lessens the probability that we would conduct type 1 error. So we can do this when we have three samples or more. So if you have two, still use your t-test. But if you have three or more samples, then we need to do an ANOVA. So the simple null hypothesis looks like this. Mu1 equals mu2 equals mu3 equals mu4 equals however many you have, right? Because we're saying that there's no difference between them. So no difference between all of these conditions. So however many conditions you have, for our example, it was four. We're going to say for the null that they're all the same. They equal each other. That's our null hypothesis. So our alternative would just be there's some difference. So for H1, the null hypothesis, more specifically, at least one of the possible null hypotheses is false. Maybe mu1 equals mu2, but it doesn't equal mu3, or it doesn't equal mu4, or it doesn't equal one of them. So at least one of them is false. So this mu1 not equal to mu2, is not equal to mu3, is not equal to mu4, is not the alternative hypothesis. With an ANOVA, we reject the omnibus null hypothesis if any one of the possible null hypotheses is true. So if any of the groups are different at all, then we reject the null. But ANOVA doesn't tell us which one isn't true. It'll just tell us if it's not true, but it won't tell us which one it is. It won't tell us which one was the most significant or which one had the most different or most increase or whatever. It just tells us that there was a difference. So we're going to pull 4 independent samples and compute the sample mean for each. So X bar 1 estimates mu1, X bar 2 estimates mu2, X bar 3 estimates mu3, etc. So if the null is true, all 4 sample means will be approximately the same. But due to sampling fluctuations, not all sample means will be exactly the same. So the ANOVA is telling us how far apart must the sample means be before we could no longer say that they're approximately equal, right? Because it's not going to be exactly the same. But it'll be close enough that we'll go, yeah, those are pretty much the same. There's no significance there. So how much difference equals significant? Well, we do that with an F-stat. And so we had been using z-scores, and then we were using t-scores, but ANOVA gives us an F-stat. So like Z and T, we have to determine the critical F-stat. So we define the critical area. And if we observe the F-stat and it's larger than the critical stat, then we could reject the null, right? If what we see is larger than our threshold for saying like this is our critical value, if it's bigger than that, then we get to reject the null. So like Z and T, F has a known distribution. Like T, but not Z. F depends on degrees of freedom. So good thing you still know degrees of freedom, right? That's n minus 1. And so that means it's not normally distributed. ANOVA is always non-directional. We're not necessarily saying like it's more or it's less. It's non-directional, but it is always positive. So there's no negative numbers for F-stats. So we can see here F equals MSB divided by MSW. MSW is the average deviation of points from the mean of their own groups. So like the average distance that Prozac points are away from the Prozac mean. Whereas MSB is the average deviation of the group mean from the grand mean. So that measures how far apart the group means are. The grand mean is the mean of all the means. So you take the average of all the group means together, the grand mean. So according to Cohen, if we have an F-stat smaller than 0.10, there's small effect. An F-stat larger than 0.10 but smaller than 0.25, we say it's got a medium effect. And then an F-stat larger than 0.4, we're saying there's a really large effect. So that's a lot of words. Let me share my screen to JASP and let me actually show you. I have JASP up. I don't. Let me actually show you what this would look like. Because whereas you've been doing some t-tests by hand, we've been doing z-scores by hand, you would not do an ANOVA by hand. That would be a whole lot. So let me share to JASP. Okay. So in your homework, you have a data file called survey1.csv. So I opened up JASP. For me, it's my recent files. If you haven't opened it recently, you might need to browse your computer to find it. So wherever you downloaded it, saved it to your desktop, we're going to open this data set. So our questions say something like, for the admittedly silly research questions below, you need to download survey1.csv. And then for each question, write down the following. You're identifying the test that you're using. So say if you're using the t-test or an ANOVA, write down specific definitions, so the null hypothesis and the alternative hypothesis or alternative hypotheses. Report the appropriate test stat, so the p-value, right? Write down the p-value that you get, and then tell me what that p-value means. Does it mean we reject the null, we fail to reject the null, there's significance, there's not? And then your answer to the following 3 research questions. So for question number 1, it says, does GPA differ significantly between males and females? So you have this big data set here that we have no idea what it's talking about, right? Because you didn't do this research or pull this data. We have things like gender, height, shoe size, if someone's a smoker, if they're right-handed or left-handed, if their mom was right-handed or left-handed, if their dad was right-handed or left-handed, their hair, maybe in inches, CDs, Greg Q, we don't know what that means, GPA, exercise, their political view, how many hours of TV they watch a day, if they drink coffee, sleep hours, how many drinks they drink, if they can tell the difference or cannot tell the difference between Pepsi versus Coke in a blind taste test, their hair color, their eye color, something about distance that we don't know about, books, studying hours, lots of stuff, right? Lots of data in here. And so our first question says, does GPA differ significantly between males and females? Okay, well, let's decide if we need a t-test or a ANOVA. So males or females, that's only two categories. But GPA, let me see what we have for GPA. Let's find GPA here. Well, it looks like there's a lot of options, right? There's 4, there's 3, there's 3.36, there's 3.6. I don't know, would that be a t-test or an ANOVA? Let's try. So let's try what we've been doing. Let's try t-test. So we have independent samples t-test. Just our most basic t-test. So you can see here we have, sorry, nope, go back. This box here. And so we're seeing there's dependent variables and grouping variables. Is something dependent upon something else? Well, we want to see if GPA is dependent upon gender. So let's find GPA. See if this is dependent upon gender. See, look, we have a t-stat, whatever degrees of freedom, and then a p-value. P equals 0.07. Is 0.07 higher or lower than our 0.05% significance threshold? And if it's more than 0.05, does that mean you reject the null or you fail to reject the null? I'm not going to tell you the answer to that because you're going to, write that as your answers in your questions. Okay, well, let's look at question number 2. Let's go back. It says, does the amount of sleep depend on one's political affiliation? So let's see. Would we do the t-test again? So is sleep dependent upon political affiliation? Let's find sleep. That dependent upon political view. Oh, the maximum number of levels is 2, but variable political view has 5 levels. I think that means we can't do a t-stat, so we need to do a ANOVA. That's right. I'm excited about it too. So let's click on ANOVA. We have some options, but just our basic ANOVA right here, analysis of variance. So if I click ANOVA, sorry, it looks the same, but it says different words, dependent variable, and then there's fixed factors. So we're seeing if amount of sleep is dependent upon political view. We have a p-score of 0.300. Is that higher or lower than 0.05? Higher. So does that mean we reject the null or fail to reject the null? Think about it. Give me an answer. You can also click on, let me see, descriptive stats. Here, if you wanted to see what the means were, standard deviations, standard error, coefficients, if you just wanted to look at the different numbers. But there's your answer there. And then for the last one, does height differ between left-handed and right-handed people? So would that be an ANOVA or a t-test? Well, I'm gonna let you do that and then write down your results. But make sure you define, let me share my screen so you can see the questions. Share. Here. So here are the questions. So tell me which test it is. So you can do number 1 and then tell me t-test or ANOVA. Give me the null and the alternative. Report the appropriate test stat. So would that be the F-score or the T-score? And then the p-value. And then tell me what that p-value means and if it does or does not differ for the first one. Does GPA differ significantly between males and females? Does the amount of sleep depend on political affiliation for 2? And does height differ between left-handed and right-handed people? And that's it. So it's not you writing down a lot of work by hand. It's just you trying to decide well, what does this mean, right? All the stuff we've been working up to all semester, putting that into JASP. You're not doing it by hand. You're not worried about the math part anymore, but can you really look through these research questions, right? And see the stats that are going on behind it and what these p-values or t-values mean and knowing which test to grab. So I hope that makes the assignment make a little bit more sense. And that's it for today.